Good evening, everybody, and welcome to this RSC public lecture. I've also been asked to welcome all those who are viewing us online. If you have any questions from the online people, if you have any questions, you can get to us via Twitter this shows me age now, using the RSC account with @RSC_comms, using the hashtag and RSC public lectures being all one word. So it gives me great pleasure to introduce Dr. Tony Bristow. I first met Tony in 1992 when he was doing his PhD at Nottingham and Trent University with one of the old contemporary mass spectrometry people. Back in the 70s, there weren't many of us, so we all kind of butt into each other quite regularly. And Tony was doing his PhD with an old contemporary friend of mine, Professor Colin Creaser. And Tony was looking at MOLDI linked to ion trap mass spectrometers. In 1995, having finished his PhD, he moved on to work at Kodak in Harrow, just up the road here. And again, he was fortunate enough to work with another one of my contemporaries, Alan Payne. And it was the first time that Tony had really been exposed to industry. And as us mass spectrometrists from industry recognise, you have customers, and your customers are usually chemists, discovery chemists or development chemists. And I'm sure Tony in them days was exposed to the delights of trying to convince chemists that mass spectrometry was equally as useful, if not more useful, than NMR, and actually the results we get were meaningful. He also broke his teeth at that time on working on chromatography as well. During that time, he did a secondment to the lab of the government chemist at Teddington, and in 2002, he moved there full-time, and he worked on a number of projects there, one of which was working out exactly what accurate mass and resolution meant across the nation, and he also worked on an MSMS evaluation between instruments and between companies, and that was quite an interesting piece of work that Tony was involved in. In 2005, he moved to where he is at the moment, which is AstraZeneca in Macclesfield, where he is an associate principal scientist in mass spectrometry, dealing with development chemists as customers there. He's the author of 26 peer-reviewed publications, and he's been asked to speak at a number of national and international meetings on mass spectrometry. He's always been an active member of the British Mass Spectrometry Society, and he was fortunate enough to be elected more or less, I think, as I was finishing my tenure. He was elected onto the National British Mass Spec Society Committee. He's been on that committee for some time now, and he's held a number of posts, a number of the offices there, and he is currently chairman of the society. He's always been interested in science and education, especially trying to get mass spectrometry out to the wider world so that people know where and how mass spectrometry impacts on our everyday life. And that's really where the title of tonight's talk comes from. So without further ado, I'm going to vacate the rostrum here and introduce Dr. Tony Bristow. The title of his talk is The Arsonist, the Martian, the Cat and the Coke, oh, and Dwain. Tony.
Thanks, Frank. Good evening, everybody, and thanks for that very, very kind and long introduction, which makes me feel quite old now, I've got to admit. So I've got a goal tonight in my lecture, is that by the end of this lecture, I want you guys all to leave the room, and all those people who are listening online, which is really starting to play with my mind, and I'm not going to think about it too much, about what on earth has arson, Martian, cats, and Coke, and our friend Dwain Chambers got to do with each other in any way at all. And that's what I'm trying to achieve, and I hope you leave the room understanding that. But before I start, there are a number of faces in the room who know me, I think, a few friendly faces, and maybe a few people, a lot of you might not know me, and maybe a few you think you might have seen me before, but I'd just like to point something out. That isn't me. I am not actually Dr. Bunsen Honeydew from the Muppets. I do seem to be turning into him as I get older, admittedly, and the weird thing is, for those who've known me a long time, I actually used to look like Beaker because I used to have that much ginger hair, but things have changed. So I digress. Let's get back to the lecture. So, arson, Martian, cat and the coke, it's all to do with mass spectrometry. And mass spectrometry is one of the most powerful analytical techniques that we have, that we use in analytical science. What do we use it for? We use it to elucidate structure and chemical properties of molecules. One of the amazing powers of mass spectrometry is its sensitivity. It's fantastic for doing trace level analysis. So in other words, measuring a very small amount of material in a very complex matrix. So that could be in a medicine, it could be in an environmental sample, it could be in food, it could be in sediment for a river. Mass spec's great at this. So in my lab back at AstraZeneca, we routinely will measure down to parts per million, maybe parts per billion levels of something we're interested in measuring. But if you go in the literature, people will quote measuring parts per trillion levels of material in the presence of a complex matrix. And that's one of mass spec's great powers. And there's very few other analytical techniques that are capable of doing that. The other great thing about mass spectrometry is I don't need a lot of sample to make my measurement. So if any of you guys happen to have an interesting white powder that you wanted analysing and you had enough to get on the head of a pin, I can take that sample on the head of that pin and I can present it to my mass spectrometer and I'll guarantee you'll get a mass spectrum from it. And that's the great thing about it. I'm not going to talk about technical mass spectrometry tonight. That would be another lecture, and probably you wouldn't necessarily find that the most interesting lecture in the world. But there's one or two key concepts I want you to take away with you about mass spectrometry. We talk about measuring mass with mass spectrometry, which is a little bit of a misnomer, really. We actually measure the mass-to-charge ratios of ions we create, which we would then present to the mass spectrometer. So I just want you to hold that and remember that. And there's lots and lots of different types of mass spectrometer that we can actually use. But to illustrate the principles of mass spectrometry, I'm just going to show you a little video of how a time-of-flight mass spectrometer works. So this illustrates the three key activities of a mass spectrometry experiment. We're going to create some ions, initially, from our molecules or our elements. For example, we're doing elemental mass spectrometry. We're going to separate those ions in our mass spectrometer, and we're going to detect them. Detectors is an ion counter. The more ions you've got, the bigger signal you're going to get. Time of flight, conceptually, is a nice, simple instrument to think about. Once we make the ions and we accelerate them out of the ion source, it's a race. So little ions get to the detector quicker than big ions do, and they're separated in the time-of-flight mass spectrometer that way. And that's illustrated in this cartoon. So we've made some ions in our ion source, and we fire them across, and you can see our little guy reaches our detector first, our medium guy reaches the detector second, and our big guy reaches our detector third. And that's manifested in the output from the mass spectrometer here. So along the y-axis, we've got intensity. And on this particular plot, on the x-axis, we've got flight time. That's very, very, very fast flight time, nanoseconds, for example. We convert that flight time into mass-to-charge ratio, and from that, we generate the data we want from the mass spectrometer. But what is it? What is this information we get from the mass spectrometer anyway? Well, we generate a mass spectrum or mass spectra. Oh, yeah. I've not told you about the way I do my lectures yet. I get a bit lazy when I talk to audiences, so I expect a little bit of audience participation, if that's okay. I will be asking questions, so my friends with the roving mics should be ready to go, and I'm hoping people will be able to answer my questions as well. So, the first question is, we have the two mass spectra here of a molecule, which is shown up in the corner. Does anybody know what that molecule is? Anyone want to venture a guess? Do you want to bring the mic down? We've got someone's offering down the front.
It's paracetamol.
It's paracetamol, correct. There's no prizes, but thank you for your answer. Yeah, so it's paracetamol. So what we've got here in this figure are two mass spectra that I've generated in one of my instruments back at AstraZeneca of paracetamol. So the top mass spectrum is generated in one particular way, which gives us molecular weight information. The mass to charge tells about the molecular weight of the compound. The bottom mass spectrum, we've put more energy into the experiment. And because we've put more energy into the experiment, that ion, our molecular ion, here our mass ion for 151, the ion has started to fall apart. It started to fragment. And those fragments we generate are diagnostic of that molecule and that ion. So the other ions we're getting here at 109, 81, 80, 53, and 43 are all we can relate back to that structure. And if it was an unknown, we'd be able to determine the structure of that ion and therefore that molecule. And that's typical sort of data we get. So in fact, mass spectrum you can think about as simply a molecular fingerprint. So we've done a little bit, I've talked a little bit about the theory of mass spectrometry, a little bit of background to the key things we need to remember about mass spectrometry. But let's get on to the interesting stuff. Let's get on to the applications. And what I really want to demonstrate to you tonight is that how these applications actually affect everybody in this room pretty much on a day-to-day basis. And I hope you go away being actually surprised by how these things actually do. So we're going to start, and we're going to talk about arson. Why are we talking about arson? Because we're talking about forensic analysis by mass spectrometry, one of the tools you can use. So this is a real case, and this data was provided by MSCAN. So if you go back a few years, there was a fire. Was a fatal arson attack in Yorkshire. And they did initial analysis of the crime scene, and they used gas chromatography mass spectrometry, and they detected an accelerant. So an accelerant would be a fuel, okay? And in this case, they wanted to know what type of fuel was used to start this fire. And the reason for that was because they'd found that the suspect in the case had been found in possession of a tub of lead replacement petrol. You don't get lead replacement petrol anymore. Something they used to get a few years ago. However, the suspect in the case who they got, their car didn't actually use lead replacement petrol, so they shouldn't have really had it. So if you can prove that the fire was started with lead replacement petrol, you naturally have a link from the suspect back to the crime scene. If you record the mass spectrum of lead replacement petrol, you get a mass spectrum of one of the additives in it. And this is a material called sulfur succinate, which is added to lead replacement petrol. And if you record the mass spectrum of lead replacement petrol, you get two key ions. So there's an ion at 421 and an ion at 18. You can see the structure of sulfur succinate on the slide as well. So if we can analyze samples from the crime scene and find these ions in the mass spectra of those samples, you're able to say that the fire's been started with lead replacement petrol, and you've got this link that you want. Now, a number of different samples were analysed from the crime scene, but the one they got interested in was the carpet extract. It's a very complex mass spectrum because it's not a pure sample. It's a mixture because you've taken this carpet extract. But you can see we've got ions at 421 and 80, and they're reasonably intense above all this chemical noise we get, and therefore we're able to say we're detecting sulfur succinate in this particular sample from the crime scene. And therefore, because of that, we've now got this link between the suspect and the crime scene. So this evidence, along with lots of other evidence in the case, this was the sole piece of evidence, was used to prosecute this case successfully. Next question. You ready with the microphones? So, what I want to know is what is the connection, as we're in London, the River Thames, racehorses, £10 notes, and a very nice river in Italy? Any idea what links those four pictures? Anybody going to volunteer a guess? Is someone other than mass spectrometry? Thank you.
Drugs, cocaine,
Drugs.
Perhaps.
Anyone in particular?
Cocaine.
Thank you. Yeah, so cocaine. So in all these places, cocaine has been detected using mass spectrometry. And there you go. Hence we got under the coke. Now, when drugs are seized, a lot of the time, the drug dealers are not really kind to the police who seize these materials and don't provide you with a nice little bags of white powder that you can analyse really easily using the mass spectrometer. Unfortunately, what you have to do is you have to probably take samples from difficult surfaces or things like vehicles and premises, and then take those samples to the laboratory and analyse them. Unfortunately, it's not actually that easy to sample from a safe or to sample from the door of a car. And we're not in the position where we can take our car, crush it up and just shove it straight into the front of the mass spectrometer. So we have to come up with novel ways of sampling. And the guys at Mass Spec Analytical came up with what I think is a brilliant idea, and it's brilliant in its simplicity. They actually worked out that you could use a clothes brush to sample things. Because as you know, we're not that long since Christmas. We'll have all been to our Christmas parties, and we've all got our suit, the guys particularly have got that suit out that's not seen the light of day for 12 months, and we'll have looked at it, and there'll be stuff on your shoulders. So you've got your clothes brush out, and you've wiped your shoulders with your clothes brush, and you know that material comes off that onto your clothes brush. And you can do exactly the same thing for sampling for mass spectrometry. So what MSA do is they take a nice new clothes brush, they take it to the crime scene, maybe a premises or a car, and they wipe around the surface with their clothes brush, put it in an evidence bag, and take it back to the lab. They also have a specially adapted mass spectrometer for doing this work. So our mass spectrometer is actually up here. You can see this is our mass spectrometer. The thing to focus on is the belt at the front. So there's a belt that's moved from the outside of the mass spectrometer into the ion source, where it's heated, Anything on the surface is desorbed into the gas phase, is ionized, and is passed to the mass spectrometer. Now, great thing about cocaine is we know that we really understand the mass spectrometry of cocaine really well. We know what ions to expect from it. So, if we tell the mass spectrometer to look for a series of ions from cocaine, every time they appear, we'll get a signal, okay, from the mass spectrometer. And that's what the data shows along in the bottom figure. So in this particular case, for samples from the glove box, the steering wheel, the door pocket, the driver's seats, the passenger footwells, and the boot, we're getting a signal for cocaine. And we're not talking about a small signal here. These are pretty impressive signals. So if anybody wants to argue with me that the cocaine hasn't been positively detected here, I don't think you win the argument. But it's a really, really neat solution to a difficult problem in terms of sampling and carrying out a forensic analysis for mass spectrometry. Martians. What on earth has Martians got to do with mass spectrometry? Well, it's all about doing chemical analysis in space. So, space-borne mass spectrometers are brilliant instruments because they can tell you so much about difficult environments in different places. So if you could take a mass spectrometer and you could drop it through the atmosphere of Venus, which can be done, and you can do real-time analysis of the Venetian atmosphere and understand what chemical components are there to make it up. You could go to a comet, and we land mass spectrometers on comets, and we drill into those comets and analyze them and look at the composition of those comets. But the key thing that they're looking for, one of the most exciting areas, is looking for small organic building blocks around the universe and the galaxy. So these are little organic molecules that if you bolt them together for long enough, you'll end up with complex organisms like we are. So if you can find evidence of small organic molecules or biomarkers out there in space, or on another planet, it's potential evidence that life could have existed on another planet in the past. It has the potential for the future. Another theory that abounds at the moment is that actually life was brought to Earth on a comet, that the little building blocks that started life on Earth were brought to us. Okay? So that's why mass spectrometry in space is so interesting. But we have a big problem. If you come to my lab, or if anyone's actually ever seen a mass spectrometer, a big mass spectrometer, the ones in my lab would pretty much fill one of these tables, anything from this high to this high. They'll weigh about 150 to 250 kilos, depending on the instrument. We have to plug them into the wall and run them off 240 volts DC. They've got great big pumping systems in to remove all the air, which you have to do for mass spectrometry. Now, unfortunately, that's not suitable for sending into space. So the first thing you have to do is take one of my big mass spectrometers, and you've got to miniaturize it. So you need to get it down from 150 kilos to a few kilos, maybe 5 or 10. And also, you have to get it into about the size of a shoebox, which is engineering-wise an incredible challenge. Unfortunately, as I said before, mine run off 240 volts DC out of the wall. You can't really do that for your spaceborne mass spectrometer unless you have an extension cable which runs to several thousand miles possibly, but obviously we don't have that. And also, you need to have very, very low power consumption. So a typical spaceborne mass spectrometer will run off 20 to 30 watts. So basically, about the same power rating as the light bulbs in this room. And sample handling. When I do my mass spectrometry experiments, I prepare my samples, I take them to my mass spectrometer, I put them on the autosampler, I set up my sequence, I set up my experiment, I press go, and I walk away, and the data's acquired for me. I then invest most of my time in interpreting that data because the instruments are so robust. Can't do that when you send your mass spectrometer to another planet. So you're not going to send an analyst with you. So the mass spectrometer's not only got to be able to do the analysis, it's also got to be able to take that sample on board and possibly manipulate it so it's suitable for the mass spectrometer as well. And finally, robustness. We've all seen images of space launches, haven't we? You've seen the amount of vibration and shaking that takes place when a mass spectrometer, when a rocket's about to take off, because of all that thrust and power that's going up through that space vehicle. So the mass spectrometer's got to be able to tolerate that. The other thing is, the pressures on other places are different. It might be exposed to ionizing radiation, so you can see how robust a mass spectrometer is going to be. And what we're going to do now, and I'm going to need a volunteer, we're going to illustrate how difficult it is to send a mass spectrometer into space. So I have a miniaturized mass spectrometer. Okay? And also, if you've got a miniaturized mass spectrometer, you need a miniature scientist. So what I need is a volunteer who's going to help me recreate a space launch. Who's willing to help me? All right. So we're going to take our mass spectrometer. What's your name?
Ben.
Nice to meet you, Ben. So we're going to take our miniature mass spectrometer, and Ben's going to place it in its housing for us. If you wouldn't mind placing it in its very expensive housing for us. And you can put the lid, don't drop it, it's very expensive. Okay. And if you put the lid on, okay, and you pick it, and what I want you to do in a second, I want you to shake that as hard as you can. But as it's a space launch, we need a countdown, okay? So in a second, I'd like you to count down from 5, and Ben's going to become an Ariane rocket and launch this into space. So you ready? 5, 4, 3, 2, 1, blast off. Great. Okay, now, thanks, Ben. Unfortunately, what Ben's done is what we don't want to happen. So my mass spectrometer is now in bits. Luckily, NASA and the other people who do this are brilliant at building these things, and that doesn't happen. But you can see, conceptually, how difficult it is to send something like this into space with it, in the engineering. So you don't want all the boards to fall apart and everything to fall apart. So thanks, Ben. Thanks very much. Round of applause, Ben. So that's the challenge. How do we get a mass spectrometer into space? And why do we want to do it? But it is done. It's been happening for a long time. We've been sending mass spectrometers into space since the 1970s, and we're getting better and better. We, as if I do it, NASA get better and better at it all the time. And the most famous one at the moment is Curiosity. So hopefully many of you will have heard about the Curiosity rover. Curiosity has been on Mars since August of last year. And in the belly of Curiosity is a chemical analysis laboratory. And within that chemical analysis laboratory, along with a number of other different types of analytical instruments, are mass spectrometers. Now, Curiosity is the biggest thing we've ever sent to another planet. It's the size of a Mini, so it's a big old beast. And what Curiosity is actually going to do is, taking a step back, and what the main aim of the experiments are in Curiosity, using the sample analysis at Mars Chemical Analysis Laboratory, is to look for these very, very small building blocks, chemical building blocks, which might indicate life may have existed on Mars in the past or have ever had the potential. So what Curiosity is going to do, it's roving around the Gale crater on Mars. If it sees an interesting feature, it has a drill. It drills into that interesting feature. It takes the sample on board. It then manipulates that sample with a sample manipulation system to get it ready for the mass spectrometry. It also has a separation device, because one of the things we like to do with mass spectrometry is if we've got a complex mixture, is to separate it into individual components before we analyze it, because it makes the data interpretation easier. So it's going to pass the samples, once it prepared them, through the gas chromatograph and into the mass spectrometer, which is shown there. So Curiosity is going to be roaming around Mars for a Martian year, which is two Earth years. It probably go for a lot longer, because inevitably these rovers do tend to keep going, even though they're designed for a certain. So watch out for the data coming back from Curiosity over the next year or two. I know they're starting to get some interesting data now. It's had a bit of a glitch recently with one of its computers, but I'm sure NASA will resolve that. So we've talked about arson, we've talked about Martians, we've talked about cocaine. What have cats got to do with mass spectrometry? And it's not about cats who drink Budweiser, by the way. Oh, crumbs have gone too far. Well, it's all to do with food scares and food protection. So if you go back to 2007, there was a big pet food crisis in the United States. There's a company called Menu Foods in Canada, and they were getting reports that their food was making cats and dogs ill. So they did some taste tests, and they were able to prove that was happening. And cats were getting very, very poorly over a period of time when they were using this food. Because of that, Menu Foods have to inform the Food and Drugs Administration in the States, and the FDA bring in lots of samples then from Menu Foods and start doing a load of testing for toxins and chemicals that might be causing this. And again, mass spectrometry as a technique comes to the fore. And you can do a really neat mass spectrometry experiment here where we do no sample prep. So actually what we can do is this experiment called direct analysis in real time. So here's our mass spectrometer where I am here. Here we have a source, an ionization and desorption source, so which we use, and we place our sample directly between the end of our ionization and desorption source and the entrance to our mass spectrometer. So we take our pet food, ionize and desorb, and look for anything in there that shouldn't be present. So when you're going to do these sort of deep food scale experiments, the first thing you need to understand is what a typical mass spectrum of a cat or dog food should be. So basically a good blank. So they'll have gone back, taken a sample from a time when there wasn't any problems, and recorded the mass spectrum of that. And that's the top mass spectrum. They then looked at some dog food, got some interesting additional ions, and the one they got really excited about was the iron at 127. If you repeat that experiment and do an experiment which we call accurate mass measurement mass spectrometry, where we measure mass to the 4th and 5th decimal place, we start to get some really important information because we can turn that mass measurement, that mass to charge ratio, into an elemental formula. And that's exactly what they did. They used a very powerful mass spectrometer called a Fourier transform ion cyclotron resonance mass spectrometer, which measures mass very, very accurately. You can see that they got the mass to charge at 127.07 and a bit. And when you take that mass charge value and you present it to the data system under certain criteria, you can get the data system to suggest elemental formulae which are consistent with that mass. So it's combinations of individual elements that will give you that mass to charge ratio. And the one they got interested in was C3H7N6, and they measured it very accurately. They also did an experiment where they broke apart the iron as well, so we got some structural information. The great thing about elemental formulae, you can search them in databases. So you can, and it's the sort of thing I do when I'm looking at unknowns at AstraZeneca. If it's something completely new to me, I'll have a look in a database and see if it suggests any reasonable structures. Because those elements, those individual elements can only be put together in a certain way to give a sensible organic structure. And when they did that, it spat out this, melamine. Melamine is also sometimes called tricyanide. I rest my case. And melamine's not very nice if you're exposed to it for a long enough period of time. It's a cumulative poison, and it causes kidney stones and kidney failure. Why was it there? It had been added to some of the raw materials that were being used by Menu Foods. It was nothing to do with Menu Foods. It was all to do with one of the suppliers. They were adding it to the whey powder to give an artificially high nutritional value to their raw material. Therefore, you can keep your raw material costs down, but sell it at a premium. Unfortunately, it kills cats and dogs. In fact, it doesn't just kill cats and dogs if you expose it for long enough. Next question. Does anybody know why this story got really scary a couple of years later about melamine? There's a couple of guys down here. You wait for...
Well, my wife's American, and she's really worried about it being in milk
yeah.
and baby food.
It was in baby food. It was in baby's milk in China. Now, the Chinese, so not only was cat and dog food being artificially spiked with melamine, unfortunately it was happening to children's baby milk in China. So Chinese government estimates somewhere in the region of 300,000 children were exposed to melamine in this, and there could have been as many as 6 deaths. So this is a very dark story, but it really illustrates how important it is, like the mass spectrometry measurements that we do for food safety and how they protect us on a day-to-day basis. But it's not just things like melamine. Brominated flame retardants. Next question. Anybody know what a brominated flame retardant is? Anybody want to hazard a guess? No? Okay. It's a molecule, it's an organic molecule that we use, which we coat furniture. In fact, a lot of you are probably sat on brominated flame retardant as I speak, because we use it to coat our furniture. It's actually used to coat the components of computers and lots of electronic devices, because the idea is that these molecules slow down the spread of fire if something catches fire. It won't stop the fire, but it'll slow down the progression of fire, give you more chance to get away from a fire situation. But what on earth is it doing in food? And unfortunately, it is there, it can be detected, and these molecules are quite nasty. If you were get exposed to them for long enough, they probably would start going through your DNA. I think the cancer-causing agents. So they have to be controlled to an incredibly low level. So you can be exposed to them, but you can only be exposed to them for a very, very small amount for a certain amount of time. Hence why the guys at the Food and Environment Research Agency up at York have been monitoring them, and they're measuring this down to 0.1 micrograms per kilogram. This is 0.1 parts per billion they're measuring these materials in fish oil. But the question is, what on earth is it doing in fish oil? How is something that's in my computer and on your seat getting in fish oil? Well, I think when we landfill stuff, over time it gets exposed to rainwater. That rainwater slowly washes these organic molecules off. It gets it in the streams, into the rivers, and eventually into the fish. But if you think about it, you're starting with not very much brominated flame retardant. You're diluting it probably thousands upon thousands of times, and then it's getting into the fish. But we can still, with great sample preparation and the sensitivity of mass spectrometry, detect these materials and make sure that we as consumers are not being exposed to them at high levels, which could do us any harm. Right, so we've done arson, we've done Martian, we've done the cat. Now let's talk about Dwain. I can't talk about mass spectrometry at the moment without talking about mass spectrometry in sport. We know we're only less than 12 months since 2012 Olympics, and mass spectrometry was to the fore during the Olympics in terms of the drugs testing that was going on. And that's what I'm going to talk about now. But I have a question. Who thinks performance enhancement, drug performance, sports performance enhancement, I've got to make sure I get this right. Who thinks the enhancement of sporting performance is a new thing? Anybody think it's new? Anybody like to hazard a guess how long we've been doing it? Just Nick.
3,000 years?
Yeah. Any particular people who started it?
The Greeks.
Greece, brilliant. Yeah, the Greeks started it. And the Greeks had a number of different ways of enhancing performance. They liked eating mushrooms. That was meant to enhance your performance. I believe reading the literature, a kilo of lamb was seen as a good thing to enhance your performance. I don't know about you lot. If someone asked me to eat a kilo of lamb and then get on my bike and go cycling, I don't think it'd work. But the interesting thing is what they used to do to dogs. So they also discovered that dogs' testicles enhanced your performance if you ate them, unfortunately. So you didn't want to be a Greek gladiator's pet, because one morning he's going to look at you and think, you can make me run faster, Fido. But the question I've always asked about this is, who thought of it the first time? You just woke up one day and know, I'm going to chop my dog's bits off and try and... Anyway, I digress. So, it's been going on a long time. This is the list of the 10 categories of prohibited substances. This is the World Anti-Doping Agency list for 2012. This is what the Drugs Testing Lab in the UK had to work to, look at monitoring these. So within each one of these categories are probably tens, if not hundreds and hundreds of individual compounds that they were looking for, which could enhance people's performance during the Olympic Games. And during the Olympics, somewhere in the region of 6,250 individual samples of blood and urine were analysed mostly by using mass spectrometry. And you could do a presentation just simply talking about people, drugs in sport. And if you ever get the opportunity to hear Professor David Cowan speak from King's, who leads all this work, please take the opportunity, because he will talk about this for hours and he's the real expert. But if you go back through history, just to put a few examples up. So for those of us who were growing up in the 70s and in the 80s, like I was, up until our friend Lance Armstrong blew him out of the water as the greatest drug cheat of all time, Ben Johnson was the greatest drugs cheat of all time. So Ben won the 100 metres Olympic gold in 1988, world record time. Within 2 days had been found to have used stanozol to enhance his performance, and was obviously stripped of the title. Through the 90s, the drug du jour was nandrolone. Lots of people got tested positive for nandrolone. Floyd Landis, I'm a cyclist, so I'm always interested in what happens in cycling. Floyd tested positive for synthetic testosterone. Right, we've got testosterone in our body, so how on earth can we differentiate testosterone that's naturally occurring in your body versus testosterone that's made in a laboratory? It's all to do with the amount of carbon-13. So the amount of carbon-13 that's in synthetic testosterone is different from the amount of carbon-13 that's in naturally occurring testosterone. And if you use a really, really powerful mass spectrometry technique called isotope ratio mass spectrometry, you can distinguish with these. It's a very, very, very difficult measurement to make, but it's an incredibly important measurement. And that's what Floyd was caught with. Now, Floyd wrote a book and for ages swore blind he didn't do it, and then admitted it later that he had all along. But there you go. And then Dwain, I mentioned Dwain because last year in 2012 for the British Olympic team, obviously Dwain had come back from his THG ban, and it was a big deal that he was going to run in the Olympics again. And speaking of 2012, you've got Nadia Ostapchuk. Nadia won the ladies' shot put and then tested positive for metanonolone, and has now stripped of her gold medal for the ladies' shot put. But she was one of a number of people who tested positive. But what's the sort of data we get from these experiments? So this is data from King's, from the drug testing laboratory. Here we're monitoring 19-norandrosterone. I think one thing that will become clear to you from all the figures is that lots of structures are quite similar because they're all based on steroidal molecules, but there are lots of other different types of molecules as well. So if we monitor, the control limit for 19-norandrosterone is 5 parts per billion. Not a lot, and that's 5 parts, and that'll be and they'll measure that either in your blood or your urine. So, and to be absolutely certain that we're detecting 19-norandrosterone, we need lots and lots of data. And we firstly have the mass spectrometry data. So we have 3 ions from that structure that we're going to monitor. So we've got 405, 225, 315, 183, and we've got to see them all. Also, we want to separate the 19-norandrosterone from all the other material that might be in your blood and urine before we analyse it. So we also have a separation device up front. I think this is gas chromatography, and that molecule will come out of the gas chromatograph at a specific time, and in this case, 6.7 minutes. So not only have we got ions that we're going to use to identify this, we've also got a time component. And so we're looking to see when we look at the real sample, are we confidently detecting 19-norandrosterone and how much is there? The thing to focus on here, this data along the y-axis, we're measuring about 5,000 in intensity, okay, for 5 parts per billion. When we take our sample that's suspicious, we have the right time, the right retention time from the gas chromatograph. We have all the ions we want to see, so we're really confident. But the key thing here is about the intensity of this measurement is about 10,000. So not only is all the ions there, but it's clearly at a higher level than the control limit of 5 ppb, so you can confidently say this sample tests positive for 19-norandrosterone and someone's been using drugs and performance-enhancing drugs in this case. And this is very typical of the work that went on for months and months and months prior, during and following the Olympic Games. Right, I'm going to move on to what I genuinely believe this is some of the most exciting things in mass spectrometry. This is going to change, I guarantee you this is going to change our lives. I really do believe this. I will warn you, if anybody's not too keen on seeing images of surgical procedures and the inside of people's bodies, you might want to turn your head away because there are some blood and guts bits coming on. So that's the same for anybody who's listening online and watching online. There are a few images coming on. And this is the work of a very, very clever man called Zoltan Takats, who's actually based down at Imperial College now. He came over from Hungary, wasn't it? I think he was working in. And he's changing the way we use, one of the people who's changing the way we use mass spectrometry. And this section of the talk is all about using mass spectrometry for both invasive and non-invasive online analysis of human beings. Okay? And we're going to start with colon surgery. Surgery, as is not surprising, is a very difficult thing to do. And being sure when you're removing a tumour that you remove only the bits you need to remove is a very difficult decision to make. And you've got to make sure you get it right. But as you can see here, there's a problem for the surgeon. Where do you dissect? So is this, obviously this doesn't look right, so is this just the tumour? But what about this thing? Is that the tumour as well? How can you be sure that you're only removing the tissue that you want to remove? Well, traditionally, that's been done by a very well-established technique called frozen section histology. So basically, you take a tissue section, and you take it to the histology lab, you stain it, and what you're looking for is the fine structure of that tissue, because the fine structure tells you about the health of that tissue. If it's all broken up, it's evidence that it's actually cancerous. It works really well, but it takes time. So it can take you anything from maybe 30 minutes to an hour to get that data back to the surgical team so they can make a decision as to whether the operation's finished or you continue. But what if you could do it in real time? And this is what Zoltan and a number of other people around the world are working on. He had sort of the realization that when you cut into tissue with either an electroscalpel or a laser, you generate material that you can pass to a mass spectrometer. So if anybody ever seen images of surgery where you get like a fine plume of material above the tissue, it's like a little mist. That mist is full of important biological information. And if you can sample that material and pass it to the mass spectrometer, you can record the mass spectra of that material. And it transpires that the mass spectra that you generate from healthy tissue and cancerous tissue are different, and you can differentiate healthy and cancerous tissue using mass spectrometry. So this is the experiment they do. So you've got an electroscalpel, it generates the plume. We have a tube that's near the electroscalpel which samples this material. There's a partial vacuum in this tube to suck it up. We use something called the Venturi effect to do this. It goes up to the Venturi pump, it's entrained in a flow of nitrogen and passed to the mass spectrometer. And what you get, effectively, for want of a better expression, this is a tissue fingerprint. And the fingerprint you get for cancerous tissue and the fingerprint you get for healthy tissue are different. So you can actually, the surgeons can just gently test different areas of tissue, look for the change and say, this is as far as we have to cut to remove this tumour. And you can imagine that's really important for any surgery, but you can imagine how important it is for something like brain surgery, where you don't want to take out too much material because you might affect someone's mental function post-operation. So this is really exciting stuff. So most of the work that Zoltan did a lot of this development was done before Zoltan joined Imperial. They are now, I've been told, they are now ramping up to start doing this in the UK, and they'll be doing some work at a hospital in Paddington in the very, very near future of online surgical analysis. So this, I really genuinely believe this is the future. And this is it. So I mentioned that mass spectrometers, we've talked about little mass spectrometers today, going to space. That's more typical of the type of mass spectrometer you might see in my lab. But as you can see, there's the screen with mass spectral data, there's a tube running to the surgical team, and that's sampling as and when they want to from by the scalpel, which you can see there, so they can decide where and when to stop their surgery. Now, that's great, but it's invasive. But it has its, it's invasive. But what if you can do we can do non-invasive analysis of the human body? When you breathe out, you are breathing out about information about your health. So you breathe out lots and lots of organic molecules. What surprised me, I was at a conference recently, and one of the pioneers in this area who was doing breath analysis for many, many years before it really took off, he recently done some work where he reckons that we breathe out somewhere in the region of 2,000 organic molecules now in our breath. Some of which, at room temperature, would actually be waxes. So what on earth they're doing in the body, I don't know. But all those organic molecules, we can use that information, metabolite information, to say something about our health. And this is where the guys at University of Leicester under Paul Monks are making massive inroads into the use of this. So using mass spectrometry as a diagnostic tool. So if you can blow into a mass spectrometer, we can tell something about the state of your health. So, for example, we know, for diabetics, that diabetics breathe out a lot more acetone than healthy people do. And you can see that here. So we've got the mass spectrometer just monitoring acetone. Our healthy subjects have some acetone in their breath. We're all breathing it out now. But our diabetic subjects have much more acetone in their breath. So you've got metabolite information about a disease state. Anybody in the audience asthmatic by any chance? Right, friend at the back, what would your doctor tell you not to do with your condition?
Smoke.
Thanks, mate. Yeah, you don't smoke. Now, what if I told you if you did smoke and you told your doctor that you didn't, that I could prove that you did?
The mass spectrometry.
Yeah, mass spectrometry. And that's exactly what they've proved. It turns out when you smoke, you breathe out a different organic molecule. You actually breathe out something called acetonitrile. So if we set the mass spectrometer to monitor acetonitrile, our non-smokers, no acetonitrile in the breath. Our smoker, big peak of acetonitrile in the breath. So they're just examples of the sort of work you can do. But like Zoltan's work with surgery and mass spectrometry in hospital, that's exactly what the guys at Leicester are doing as well. They now have a mass spectrometer in the A&E department of Leicester Royal Infirmary. And they've got, along with the mass spec, they've got lots of different tools in there. They've got some vibrational spectroscopy. They've got imaging instruments as well. But one of the tests you can do when you go in, you'll be plugged into the mass spectrometer, you'll breathe out, and they'll look at what your metabolites are saying about you. So it might tell you something about whether you've got an infection, whether we know that, for example, that for things like early stage lung cancer, your metabolite profile changes. You could use it as a diagnostic tool for things like that. And then also drug overdoses would easily detect the drugs in people's mouths and breaths. And it just keeps. This is hot. This is January 2013. So this was taken from the BBC website earlier this month. So there's a research group out in Canada, and the work they're doing, they've been able to demonstrate that not only can they detect bacteria, but they can differentiate the types of bacteria because the metabolites from different bacteria give different mass spectra. And they've done this by basically connecting someone to the mass spectrometer, getting them to breathe, and they can differentiate these different types of bacteria. Why is that useful? Because it helps you decide what treatment to put somebody on. Because different bacteria respond to different treatment. But to finish, I'm just going to move off the subject of mass spectrometry very slightly, but to bring home the whole concept of you as an audience being analysed. So, audience, who's been to the airport recently? Okay? At any point, or any time, any point, if any of you have, when you've gone through X-ray, started picking up your bags, ever had someone come along with a little cotton wool swab and wipe your bag? Yeah? Yeah? Great. What they do with that is they take it to a device called an ion mobility spectrometer, which is a little bit like mass spectrometry, but it has some conceptual differences. And that's that device up in the top left-hand corner as you guys are looking, the ion scan device. They put it onto that device, it's heated, any material on that will be dissolved into the gas phase and ionized and separated from various other components. It's designed to look for explosives and drugs of abuse. If this device goes ping, you ain't going on holiday. Well, you are once you've explained the situation. And that's an offline one. But has anyone seen one of these big blue devices at the airport yet? The Smiths Industries devices. That's a walk-in ion mobility spectrometer. So this is basically do total body analysis for drugs of abuse and explosives. If you walk in, you get air shot at you from every direction. And that might be one for ladies, actually, if you're going to the airport, maybe not wear a skirt. Air shot at you in every direction. That air is sampled, concentrated, and passed to the ion mobility spectrometer. And they get a reading, and it tells you about whether they're detecting evidence that you've got drugs of abuse or explosives. Now, the slight problem with this technology is, though it's incredibly fast, it's not that specific, so you do get some false positives. And I was doing this talk to a student group at AstraZeneca who came in, and I asked about ion mobility spectrometry, and this young lady put her hand up and said, "Oh yeah, I've heard of that thing." I said, "Why is that?" She said, "Oh, they got my grandma with it at Newark Airport." And then she'd mentioned, and she's a vicar, so I did really feel sorry for her. But what they'd actually detected was her medication. It had a similar signal to, say, a drug of abuse as her medication is. So they very quickly worked out that she wasn't the world's leading drug dealer, but she was a nice little old vicar from London. But it just shows you. But I think, though this is very powerful, this is where mass spectrometry might have an opportunity in the future because of its specificity and selectivity to start doing this type of work. But watch out for that. Next time you go to the airport, when you get to the end of the X-ray, have a look for those. And that's pretty much everything I've got to say tonight. I'm very honoured that lots and lots of people I've met over the last few years, because when I go around conferences, I do like to collect material to come and talk to groups like you guys about the wonderful stuff that's going on in mass spectrometry. So the particular people I'm going to thank tonight are Zoltan Takats at Imperial, Paul Monks at Leicester, Simon Hurd at CS, at Ferrer as it is now, Richard Sleeman at MSA, Brian Gamble from USA Food and Drugs Administration, Dave Cowan at King's College, and Will Brickerhoff, who actually gave me all the information that I've got talking about Curiosity, who came over last year to talk for a conference with me from NASA. I hope that I've achieved my goal, that you all now understand what the link between the Arsonist, the Martian, the Cat and the Coke and Dwain is. I hope you found it enjoyable. I hope I've been able to prove to you that mass spec is affecting our lives. And finally, I hope I've been able to demonstrate to you that mass spec is going to affect our lives even more in the future. And maybe one day, because mass spectrometers are being miniaturized, you'll go to your doctor's surgery and you'll sit down and you'll have your talk about what you're ill and you'll blow into a mass spectrometer and you'll do a quick diagnosis, say, actually, we think you've got this in it. I do genuinely believe that's coming in the future. So thanks for your time and thanks for listening.
Thanks, Tony. Thanks, Tony, for a really, really interesting talk. We've got time for some questions. There are two ladies wandering around with microphones, so please wait till one of those gets to you before you actually ask the question. Okay, do we have any? Oh, we have some Twitter onlines as well. So we'll take the Twitter one first.
Wow.
Okay, so steroids are big fatty molecules that may often be ill-inclined to ionize. Yeah, these are mass spectrometers.
Yes.
Are there any known substances that sportsmen may use to enhance their performance that do not lend themselves to mass spectrometry? Eliza from Cambridge. There you go. Yes, okay. Steroids are big fatty molecules that may often be ill-inclined to ionize. Are there any known substances that sportsmen may use to enhance their performance that do not lend themselves to mass spectrometry analysis?
I suppose the answer to that is possibly. However, I think what we're very good at as mass spectrometrists is constantly redeveloping the ways in which we ionize molecules. So if I think about the range of molecules that I encounter at AstraZeneca, and I can encounter the smallest building block in chemistry, so that might be a small aromatic organic, all the way up to incredibly complex polymeric systems that we use to turn our drugs into medicines, analytical nucleotides, and bits of protein. There's very few I can think of that we'd struggle to do, unless it was the only challenge would be it was very, very, very large in molecular weight, and that might not necessarily be the ionization issue. It might be whether we can actually do anything with the mass spectrometer. So I'm sure someone knows better than me, and there might be one or two out there, but my experience is we've got so many tools, we'll always find a way.
Yeah, I agree. I think you can always ionize them in some way, shape or form. Question there.
Given the sensitivity of this, is it possibly true that each individual has their own spectrum of chemicals that they breathe out, and you could use this for individual identification?
That's a brilliant question. I really don't know the answer. I mean, honestly, I suppose I genuinely don't know whether that's possible. I'm sure there are people who are looking at, and the metabolite guys are, the metabolomics and metabonomics guys are looking at that, but that is one I'd have to refer to people who've got a greater expertise in that area than I do. But it's not beyond the realms of possibility. But the challenge you've got is how do you validate the measurement? Because you've got day-to-day variability, and so but it's, then again, you know, we couldn't do DNA sequencing a few years ago, so why not?
Yeah, because I envisage a time, I think, when you can get to the well-being clinic, the sports gym, where you can almost sample a urine every time you go there, and then build up a standard database that says this is your diurnal profile, and then if things kind of change over time, I believe we can get to that place. Yeah. Any other question? One there.
Can you explain to me? Can you explain to me, please, why, if I'm synthesizing testosterone in my body, why using sort of the same building blocks, I can't make the same testosterone in the lab? Because
your carbon, it's the carbon source. It's the source of carbon you're using is subtly different in your body to the source of carbon you'll be using in the laboratory. That's what it's down to. So it's all to do with how much carbon-13. So I'll answer it in a different way. So for example, you can tell where heroin's grown by isotope ratio mass spectrometry, because the amount of carbon-13, because it's an environmental factor, the amount of carbon-13 in heroin that's produced say in Iran is different from Pakistan and is different from other places around the world, and you can distinguish it. It's actually the environmental factors that affect your body and the source of carbon you'd use to synthesize it, and the amount of carbon-13 will be different.
Doesn't this come from carbon dioxide in the air?
Yeah.
That's what the university dispersed.
I don't know. I'm not sure. But it's from a mass spectrometry view, you're measuring different levels of carbon-13, and that's how you distinguish it. And it's very well established and very well validated. That is the case. Sorry, I haven't got a better answer, but that's why now.
It's a question just there.
Yeah.
Yeah.
It's not actually a question. It's an answer to that particular one there. For a long time, and they've even been able to do this by NMR, but certainly you can do it by ion ratio mass spec. You can tell whether somebody's adulterated grape juice with sucrose from sugarcane or beet in order to make wine. So you can tell whether the wine has been made out of grapes or grapes plus sugar.
You could do the same with honey. Exactly the same, looking for adulteration. That's where it's just the natural variations from different places. Is that okay?
Yeah.
It's not a perfect answer, but...
Any more questions? I've got one just to finish up with then, Tony.
Oh, hang on.
Another one. Whoa. Twitter's on. What are the limits of detection for a continuous real-time measurement? Can it handle corrosive gases?
Yes, it can do. And again, for real-time measurements, you can... There are a number of instrument vendors make gas monitoring devices which will measure down to parts per billion level quite readily. And that's probably fair.
So just a question. You were talking about miniaturizing mass spectrometry and being able to put it out into outer space. You then talked about the analysis of sportsmen. Mm-hmm. Yeah. Do you ever envisage the day where... So, for example, the girl that got her medal taken away from her because she was positive, that was a few days later. Yeah. Can you envisage the time where mass spectrometry, rather than being remote and the samples go to the mass spectrometer, where the mass spectrometer is sitting on the start line?
It's not beyond the realms of possibility. I mean, because we're to exemplify that from Frank's question, we are now coupling mass spectrometers direct to chemical processes because we want to see what's happening in real time, and that's using small portable instruments. There's no reason why with the right sample, some appropriate fast sample prep, and with the right device you couldn't do it.
So you could have grabbed Lance Armstrong before he started.
Let's catch him first.
Any other questions?
Yeah.
One there.
So presumably it's quite expensive to have a mass spectrometer.
Yes.
Like a huge amount of money. Is there a time in the future when they maybe wouldn't be so expensive, so they could be used in...
Well, absolutely. So my instruments that I've got will range from anything from commercial instruments, anything from 70,000 to, if you go to one of the big ones, maybe £500,000. However, the new miniature instruments, and it still sounds expensive, are getting down to about £30,000. But that's a big step down because as you get better at making them and refine the engineering, you can. There's some incredible miniature instruments which are basically the size of, there's some actually the size of mobile phones now. So I believe we will get there because you can miniaturize the components. And in fact, you can make the components you could make the components actually things that you can put in and replace. So I think that the sub £10,000 mass spectrometer, which still sounds relatively expensive, is coming, and that will continue to decrease in price. Yeah, I honestly, one thing I've said a couple of times when we've done this presentation is that it's not beyond the realms of possibility that your mass spectrometer will be an iPhone app one day. But the response to that from one lady was, what are the hypochondriacs going to do? And it was an interesting concept. If you can self-diagnose, people like self-diagnosing with the internet, can you imagine having chemical analysis to do it? So it has probably some moral implications as we go smaller, but we will get there, definitely, convinced.
Okay, if there are no more questions, I'd just like us all to thank Tony in the usual way, and tea and coffee is served in the room outside.
Sorry, before you all disperse, for those that haven't yet read the programme, we do